So, in this class, we shall be discussing with some problems related to Heisenberg's uncertainty principle. Now, we already know that the three major forms of uncertainty principle, delta x, delta px greater than equals h by 4 pi. So, this is equation 1. We also know that delta x into delta Vx greater than equals h by 4 pi m. So this is the second form. That means it is never possible to determine the position and momentum of a microscopic particle simultaneously with equal degree of accuracy. Also, it is never possible to determine the position and velocity of a microscopic particle simultaneously with equal degree of accuracy. Similarly, there is another expression, that is delta E into delta T greater than h by 4 pi, where, if you remember, this is the uncertainty in the determination of energy. Uncertainty in determination of energy of the microscopic particle, and this is the uncertainty in determination of time. So this is the third form of uncertainty principle. So uncertainty principle is applicable between any two conjugate properties whose unit will be joule second or arc second, isn't it? Joule second or arc second. Now we know that E equals h nu, where delta E, this is the uncertainty in the determination of energy, will be equal to h is a constant, h delta nu. So instead of uncertainty in the determination of energy, uh, they can also give you the uncertainty in the determination of frequency of the microscopic particle, isn't it? So delta nu, this is the uncertainty in determination of frequency of the microscopic particle. Okay, so using these three forms of uncertainty principle, we will discuss a few problems. Okay, so first of all, going to next page. See problem 1. A measurement establishes a measurement establishes a measurement establishes that the position establishes the position of a proton with an accuracy of with an accuracy of plus minus 1.0 10 to the power minus 11 meters. Okay, accuracy of 1.0 10 to the power minus 11 meters. Find the uncertainty in the proton's position. Find the uncertainty in the proton's position after 1.0 seconds. After 1.0 seconds, given that mass of proton equals 1.672 10 to the power minus 27 kg. So this is the problem. A measurement establishes that the position of a proton with an accuracy of 1.0, sorry, with an accuracy of this, find the uncertainty in proton's position after 1 second. তার মানে এখানে uncertainty in the determination of position initially, মানে when t equals 0. Okay, মানে at the time of measurement, let it be delta x 0. This is plus minus 1.00 10 to the power minus 11 meters. This is plus minus. What does it mean? It means that this is from 1.00 to plus 1.00. অর্ডারটা হচ্ছে 10 to the power minus 11 meters. So what is the actual uncertainty? This is delta x 0. So this is actually 2 into 10 to the power minus 11 meters. One should expect that it will be 2. See, whether it is 2 or 1 doesn't matter, because it is of the order of 10 to the power minus 11. Okay, so since it is of the order of 10 to the power minus 11, so this is delta x 0. Now we know that delta x into delta p x greater than equals h by 4 pi, or delta x, better let me write delta vx, delta vx by m, h by 4 pi m. So initially, where at time t equals 0, this is 0, delta vx. So let us find out the value of delta vx, uncertainty in the determination of velocity. So delta vx equals h by 4 pi m delta x 0. So if you substitute these values, you can substitute these values, whatever it is. So I'm not substituting it directly. So let it be equation 1. So this is the uncertainty in the determination of velocity initially. Now you are asked to find out the uncertainty in the position, proton's position after 1 second. Okay, now we know that velocity vx, this is given by x by t, isn't it? This is given by x by t. Or uncertainty in the determination of velocity, that means delta vx, this will be given by uncertainty in the determination of position of the particle by time. Okay, so we can write delta x equals t delta vx, t delta vx. So this is equation 2. Now let after, so this is what? This is the uncertainty in the determination of position after t seconds. This is the uncertainty in determination of position of the microscopic particle, of the proton here, after t seconds, isn't it? So we have related this with the uncertainty in the determination of velocity. Now we already know the expression for the uncertainty in the determination of velocity. This is the expression. So we can substitute this expression in equation 2. Delta x, this equals greater than equals delta v যখন বসাচ্ছি, delta x greater than equals t h by 4 pi m delta x0. So this is the expression for delta V. So delta x will be, here t is 1 into 6.626 10 to the power minus 34 divided by 4 into 3.14 into mass of the proton. This is given 1.672 10 to the power minus 27 10 to the power minus 27 into, what is delta x0? 1.0 10 to the power minus 11. This is the value of the uncertainty initially. So you can calculate this value. So in my calculation, you can check the calculation, please. This will be whatever it is. This will be greater than equals. The order should be 10 to the power 3. Please find out this value. It has something into 10 to the power 3 meters. So this is the uncertainty in the determination of position after 1 second. Please check whether it is correct or not. Please see the calculations. Now let me give you the second problem. A hydrogen atom, a hydrogen atom is 5.3 10 to the power minus 11 in radius. Okay, atom in radius, using uncertainty principle. Using uncertainty principle, using uncertainty principle, estimate, using uncertainty principle, estimate the minimum energy, estimate the minimum energy, estimate the minimum energy an electron can have, an electron can have in this atom, in this atom. Okay, তাহলে দেখো আমরা এটাকে সলভ করি। So what are the informations provided? Informations কি কি দেয়া আছে দেখো। Hydrogen atom, this value is given, this radius is given to be 5.3 10 to the power minus 11 meters. So you see, this is basically the radius of first Bohr orbit. Okay, you know that this is 0.05 something 9 into this angstrom. This is close, this is practically 8, right? So the radius is equal to, this is the first Bohr radius. Now see, the electron, electron is present here. Now the question is, if I say this is the uncertainty in the determination of position of the electron. So this is the uncertainty in determination of position. This is the uncertainty in determination of position of the electron. So the electron can be present এইখান থেকে এখানের মধ্যে আমি যদি বলি কোথাও না কোথাও ইলেকট্রনটা আছে. The electron may be present within this range. So this is the uncertainty in the determination of position of the electron. Now the question is whether this uncertainty is high or not, or low. The answer is it is extremely low. This value is extremely low because this is the first Bohr radius and the atom is much larger than first Bohr radius. So the uncertainty in the determination of position is small with respect to atomic size. It is small with respect to atomic size. Okay? So you are provided with this value and you are asked to find out the minimum energy an electron can possess. Now, in terms of energy, see if you write this equation, delta x, delta px greater than equals h by 4 pi. So from here, এখান থেকে আমরা বলতে পারি যে delta px, we can find out the value of delta px greater than equals h by 4 pi delta x. So this greater than equals 6.626 10 to the power minus 34 joule second divided by 4 into 3.14 into delta x টা 5.3 10 to the power minus 11. So as per my calculation, this value is 9.9 10 to the power minus 25 mk's unit, অর্থাৎ kg meters per second. So as per my calculation, this is 9.9 10 to the power 8. Now the question is whether this uncertainty in the determination of momentum is high. The answer is it will be high. Why? Because as per the uncertainty principle, try to understand, as per the uncertainty principle, if the uncertainty in the determination of position is small, if the uncertainty in the determination of position is small, then uncertainty in the determination of momentum, this has to be high as per the uncertainty principle. তাহলে এটা high হচ্ছে, high কার রেসপেক্টে? with respect to the momentum of the electron. কার রেসপেক্টে high হবে? it is high with respect to the momentum of the electron. কেন বলছি? Because if you calculate the momentum, you know it is mass into velocity. This is of the order of 10 to the power minus 31 and this is of the order of 10 to the power minus 10 to the power 6, sorry, 10 to the power 6 meters per second. So the order of this is 10 to the power minus 25 mv. বুঝতে পারছো মোমেন্টামের যে ভ্যালুটা, this is the value of the momentum and this is the uncertainty. মানে if the value of the momentum and the uncertainty, they are same, then obviously this value of momentum is very high. Please try to understand, if the value of the momentum is equal to its uncertainty, then this value of momentum, if it is equal to its uncertainty, then the uncertainty in the determination of momentum is very high. তার মানে যে কারণে আমরা বলছি this is very high. আবার অন্যভাবেও বলছি, দেখো, since this is very small, this has to be very high. Okay, now if this is high, then we can approximate this. Since the uncertainty in the determination of momentum is high, since delta px is very high, ঠিক আছে, এটা যদি হাই হয়, we have delta px nearly equals the momentum. So this greater than equals, যে ভ্যালুটা বেরিয়েছে 9.9 10 to the power minus 25 kg meters second inverse. So we can write this is the value of the momentum. Right, so greater than equals, therefore kinetic energy, you know that this is equals p square by twice m. So greater than equals, এখানে 9.9 10 to the power minus 25 square by 2 into 9.1 10 to the power minus 31. So this kinetic energy greater than equals, এটা আমার যা আসছে দেখো 5.4 10 to the power minus 19 joules. So greater than equals means minimum kinetic energy টা তাহলে কি হবে? The minimum kinetic energy will be equal to 5.4 10 to the power minus 19 joules. Right? So if you want to transform this into electron volt, this will be greater than equals 3.4 electron volts. আমরা জানি যে 1 electron volt equals 1.6 10 to the power minus 19 joule. So you can convert this into electron volt. Okay, so this is the minimum value of kinetic energy. Okay, minimum value of kinetic energy of the electron. So let us move to another problem. Say an electron is confined. An electron is confined in a one-dimensional box. An electron is confined in a one-dimensional box of length 10 centimeters. Is confined in a one-dimensional box of length 10 centimeters. Find the uncertainty. Find the uncertainty in determination of its velocity. Find the uncertainty in the determination of its velocity. Questionটা দেখো ভালো করে. Please look at the question carefully. Say an electron is confined in a one-dimensional box whose length is 10 centimeter. So this is the uncertainty in the determination of position, 10 centimeter. Okay. So find the uncertainty in the determination of its velocity. Very simple. Greater than equals h by 4 pi m. So delta Vx greater than equals h by 4 pi m delta x, or delta Vx greater than equals 6.626 10 to the power minus 34 divided by 4 into 3.14 into mass of electron. Mass of electron হচ্ছে 9.1 10 to the power minus 31 kg, and delta x হচ্ছে 0.1 meter. তাই তো? And you'll find that this value is 5.8 10 to the power minus 5 meters per second. See, with respect to the electron, try to understand, with respect to the electron, this value of uncertainty is very high. That means the position of electron cannot be determined. You cannot determine the position of the electron, isn't it? But if you look at the uncertainty, see the value, uncertainty in velocity. The velocity is of the order of 10 to the power 6 meters per second. And this is very small with respect to the value of velocity. So since this is very high, because it is 10 centimeters, so this uncertainty in the determination of velocity is very small. Okay, so this is a very simple problem. So let us move to another problem. This is with respect to energy and time, uncertainty in the determination of energy and time, the next problem. Okay, let me give you the problem first. See, an excited electron, an excited atom, an excited atom gives up its excess energy, an excited atom gives up its excess energy by emitting a photon by emitting a photon of characteristic frequency, by emitting a photon of characteristic frequency. The average time period, the average time period that elapses, the average time period that elapses between excitation of the atom, between excitation of the atom and the time it radiates, and the time it radiates, and the time it radiates is 1.0 10 to the power minus 8 seconds. Find the inherent find the inherent uncertainty in frequency of the photon. So please try to understand the question properly. Please read through the question. See, an excited atom gives up its excess energy. What does it mean? Excited atom means if this is the ground state, this is the excited state. So an electron is excited. I mean, the electron is actually transferred to the excited state. So when the electron is in the excited state, we are saying that the excited atom, so the electron is in this level, it emits, excited atom gives up its excess energy by emitting a photon of characteristic frequency. That means this excited atom, now what happens? It actually emits a photon of characteristic frequency. When will it emit a photon? When it will come back to the ground state. You know that this E equals h nu, right? So, of characteristic frequency. This is the corresponding frequency. So, by emitting a photon of characteristic frequency. Now the average time period, see the average time period that elapses between excitation of the atom and the time it radiates. That means the average time period that elapses between, see this process of excitation and de-excitation. This is given by eta. So we can say that the uncertainty, this is very small. So we can say uncertainty in the determination of time for this process. This is given by 10 to the power minus 8 seconds. 10 to the power minus 8 seconds. So you're asked to find out the uncertainty in the determination of frequency. This one, frequency. You're asked to find out the uncertainty in the determination of frequency. Now, by using uncertainty principle, we know that delta E into delta T greater than equals h by 4 pi. Now, we know that E equals h nu or delta E equals h delta nu. So, we can write that instead of delta E, we can write h delta nu into delta T greater than equals h by 4 pi. So, therefore, delta nu greater than equals 1 by 4 pi delta T. Okay. So, you can calculate this. You'll find that it will be approximately, it will be 8 into 10 to the power 6 hertz. So, this is the uncertainty in the determination of frequency. That means, if since the uncertainty in the determination of time for the process, see, this is very small. So the corresponding uncertainty in the determination of frequency, it will be high. Uncertainty in the determination of energy and frequency, both will be high because this is very small. Okay. So since this is very small, the uncertainty in the determination of frequency is very high. So that is why from this problem, we can explain the broadening. We can explain the broadening of spectral lines. Now, a broadening of spectral lines. Normally, from Bohr's theory, you have seen previously in your +2 level that you get these type of lines. Line spectra is obtained. Gradually, the energy gap decreases and ultimately we get a band like this. Now, even for these lines, okay, even for these lines which are supposed to be just, I mean, discrete lines, even it was observed that these lines are not discrete, these are quite broad. Okay, so the lines are broad. What does it mean? That means there is some uncertainty in the determination of their frequency, isn't it? There is uncertainty. So this is the frequency axis, suppose. So there must be some uncertainty in the determination of their frequency. Now, why there is uncertainty in the determination of frequency? Since delta t is very small, delta E or delta nu will be very high, and that that is why there occurs broadening of the spectral lines. The spectral lines, which are supposed to be lines, okay, they are quite broad. So this is how we can explain the broadening of spectral lines, which I mean, in the electromagnetic spectrum, maybe in the visible region itself. Okay, fine. So let us move to another aspect. See, from uncertainty principle, we can have an idea. তাহলে আমরা next যেটা বলবো, that is concept of electron cloud, or probability of finding an electron, concept of electron cloud or probability of finding an electron from uncertainty principle. So we can have an idea. In fact, the uncertainty principle first gave an idea about the fact that electrons, they are just not particles localized in a specific orbits. We can actually we can explain the electrons from probabilistic concepts. How? See, if you look at the Rydberg constant for hydrogen, this is 109,677.8 centimeter inverse, and this Rydberg constant of hydrogen, it has been determined quite accurately. So the Rydberg constant, it has been determined quite accurately. Okay. Now let us write down the expression for energy of an electron from Bohr's theory. We know that this is minus twice pi square z square e to the power 4 m divided by n square h square ergs per atom. So this is ergs per atom for a given atom. Now, if we want to write it in terms of Rydberg's equation, so this is in, of course, in the CGS unit. You can also write this in MKS unit. So if you write down the expression for Rydberg's constant, twice pi square e to the power 4 m divided by ch cube. This is Rydberg constant. Now, so this has to be multiplied by ch divided by n square to achei or z square. So we can write the expression for energy like this in terms of Rydberg constant. R c h z square by n square. So this is an expression for energy in terms of Rydberg constant. Say this is for hydrogen jodi hoy RH. Okay. Now, since the value of this Rydberg constant has been accurately determined, see, for hydrogen atom, we know that Z equals 1, N equals 1, ground state. The value of C is constant, 3 into 10 to the power 10 centimeters per second. And the value of Rydberg constant, this is also constant. Right, so 6.626 10 to the power minus 27 arc second, if you want to express this in CGS unit. So, what I am trying to say is, if the value of Rydberg constant is accurately known, then the energy associated with the electron can be determined accurately, isn't it? So, since RH is accurately known, since RH is accurately known, the energy associated with the electron in hydrogen atom can be determined accurately. তাই তো, তাহলে আমরা এনার্জিটা accurately determine করতে পারবো. Now we know that this energy, kinetic energy, this equals p square by twice m. Now if we can calculate the total energy accurately, we know from Bohr's theory that this total energy, this equals EP plus EK, right? And this EP and EK, they are related. You know that this total energy jeta hocche, total energy সঙ্গে এই EK আর EP, they are related from Bohr's theory. So since the total energy is accurately known, so kinetic energy can be determined accurately. So therefore momentum of the electron can be accurately determined. Momentum of the electron can be accurately determined. See, if the momentum of the electron is accurately determined, then the position of electron cannot be determined accurately. Then the position of the electron cannot be determined accurately, isn't it? If the momentum is accurately determined, then the position of the electron cannot be determined accurately. What does it mean? See, diagrammatically we can write like this. Say Since momentum is determined accurately, then we cannot determine the exact position of the electron with respect to the nucleus. We can say that the electron is the position of the electron, the uncertainty. The uncertainty is high because we cannot determine the position accurately, isn't it? So there is a wide range, there is a wide range of distance in which the electron may be found out. So instead of drawing specific circular orbits for the electrons, so this is an orbit with minimum radius. So this is another orbit with much higher radius. So there can be so many orbits because there are so many different positions of the electrons. So the electron can be present in any of the orbits. So instead of drawing orbits like this, we can say that this is the probable region of finding the electron. This is the region. This is the probable region of finding the electron around the nucleus. And this led to the concept of electron cloud. Also, the electron is not actually localized at a specific region, at a specific orbit rather. It is not moving around a specific orbit, but it may be present over a wide region in space. So this led to the as if this is the electron cloud. This is the electron cloud, or the region of probable location of the electron, and this gave an idea about atomic orbitals. This gave an idea about the atomic orbitals. So from uncertainty principle, we can have an idea about the region of probable location of the electron, or the orbital, or the concept of orbital. Okay, so let us come to another problem. Calculate, say, calculate the uncertainty in location. Calculate the uncertainty in location of a photon of wavelength 6000 angstrom unit, assuming that the uncertainty in wavelength is 1 parts per million. Uncertainty in wavelength is 1 part per million of the actual wavelength. Okay, so what is the meaning of this problem? Just try to understand the problem properly. You are asked to find out the uncertainty in location of the photon. তার মানে তোমাকে কি বলেছে, ডেল্টা এক্স টা বার করতে বলেছে, আনসার্টেনটি ইন দি ডিটারমিনেশন অফ পজিশন, লোকেশন কথাটা বলছে মিন্স you are provided with wavelength which is 6000 angstrom unit. So uncertainty in the determination, this is 1 by 10 to the power 6, 1 parts per million. into 6000 angstrom unit. So we can say this is 6 into 10 to the power minus 3 angstrom unit. So you are provided with the uncertainty in the determination of uncertainty in the determination of wavelength, and you are asked to find out the uncertainty in the determination of position. দেখো আমরা যে uncertainty principle পড়েছি, we know that P equals h by lambda. We know that P equals h by lambda from de Broglie. From de Broglie, we know that P equals h by lambda. So we can say delta P, uncertainty in the determination of momentum, equals, আচ্ছা এখানে আমরা লিখতে পারি দেখো delta P, uncertainty in the determination of momentum, we can write that this equals এইভাবে লিখি আমরা, therefore P, আমরা যদি বলি delta P equals uncertainty in the determination of momentum, then we can write like this: P minus delta P equals h divided by lambda minus delta lambda plus, sorry, because see this is inversely proportional to wavelength. So if I subtract this with the uncertainty of momentum, then uncertainty in the corresponding wavelength should be added, because there is an inverse proportion. So if you subtract this, then this should be added. Now using these two equations 1 and 2, now if you add these two, এই দুটো আমরা যদি add করি দেখো, so if you add these two বা subtract করলে দেখো কি হচ্ছে, if you subtract these two, delta P, this will be given by h by lambda minus h divided by lambda plus delta lambda, or delta P equals h lambda plus h delta lambda minus h lambda divided by lambda into lambda plus delta lambda. তাই তো? So from here we can write that delta P equals, দেখো এটা কেটে যাচ্ছে, h delta lambda divided by lambda square, nearly equals, because this is very small, we can neglect it. ঠিক আছে তো? So the expression, so we have derived the expression for the uncertainty in determination of momentum with uncertainty in the determination of wavelength. So this is the relation between uncertainty in the determination of momentum with the uncertainty in determination of wavelength. Now by using see, you are asked to find out what, এইটা বার করতে বলেছে, আমি এইটা বার করতে বলেছি, কিন্তু আমি যে কারণে I have actually found out the uncertainty, because you can combine these two, uncertainty principle এর এই দুটো আমরা ইউজ করতে পারি. So using uncertainty principle once again, we know that delta x into delta px greater than equals h by 4 pi, তাই তো? তাহলে delta x into h, substituting this value, delta lambda by lambda square greater than h by 4 pi. ঠিক আছে? So delta x, so from here we can say delta x greater than equals lambda square by 4 pi delta lambda. Right? So this is the expression we can use for determination of uncertainty in position. তাই তো? তাহলে দেখো এইটা, this is 6000 into 10 to the power minus 10 meters. ঠিক আছে তো? সো মানে অ্যাংস্ট্রম মানে হচ্ছে, হ্যাঁ, আর এইগুলোকে তুমি অ্যাংস্ট্রমে করে দিলেই তো হয়, অসুবিধা কিছু নেই। Directly you can express this in angstrom, and you can find out the value. You can find out the value in angstrom unit. Can you follow this? Because see, this is, look carefully. See, this will be in angstrom square, and this will be in angstrom, isn't it? So you substitute these values. You know this value lambda square এর ভ্যালুটা তুমি জানো এটা, আর delta lambda, you know this value. You substitute this value and find out delta x in angstrom unit. Okay, so I'll stop today.